So we need to pick up, how ironically, we are done talking about snow and we're ready to talk about actually warm clouds. Yay! So a cloud is basically a chunk of air that has risen and cooled and is cooled to the point, it's cooler than the dew point temperature, so you have condensation going on in that parcel of air. Oh, hi, John.
Hi.
And so let's just say that you don't have ice crystals form. Well, you need to go ahead and in order for it to rain, we're going to talk about something instead of the Bergeron process called the collision coalescence process. And we talked about two types of condensation nuclei, hygroscopic and hydrophilic. Okay, the water-loving and the water-phobic. And so these hygroscopic ones are basically ready to get the party going with regard to making little tiny droplets of liquid water. So the thing about those little liquid droplets of water is that they will go ahead and start falling within the cloud. Now, when we start to talk about severe weather, we're really going to hit it hard, but I'm going to introduce you to this idea that there is an ongoing updraft. Okay, kind of like basically everywhere, okay? Gentle little bit of breeze, that's the updraft. So there will be little droplets of water falling down, and they will accelerate at the acceleration due to gravity. I think we might have talked about this before. But actually, if the air weren't there, they'd keep going faster and faster, 9.8 meters per second faster every second they fell. But since air is there, eventually that air will make it end up with what we call its terminal velocity. Okay, so it's as fast as it's going to fall. It basically tops out at a certain speed. You don't look like I have to convince you over that. But some people are like, no, things keep going faster and faster. I'm like, well, no, not necessarily. And it's an aerodynamic thing, right? So with regard to liquid water droplets, the deal is that the smaller they are, the lower their terminal velocity. So the smaller ones drag through like this. The larger they are, the faster they're going to fall. Okay, so the little ones, you're looking at terminal velocity of 0.006 miles per hour. The larger raindrops, you're looking at 20 miles per hour, their terminal velocity. So the larger ones are falling faster than the smaller ones. That's the dynamics that's happening up in that cloud. And here's everything in between. Okay, so the big ones are falling faster than the smaller ones. Now, in order for it to successfully leave the cloud, here's the word updraft. Okay, and usually it's kind of gentle. Okay, actually, not only gravity, I should say, has to overcome that little updraft. Okay, so in order to fall from the base of the cloud. So it has to have a certain mass in order for gravity to kind of say, all right, you're on your way out. So it basically gets larger via this, the term was collision coalescence process. You saw a minute ago, collision coalescence, that's what makes it larger. Okay. And it's really, the term collision coalescence is great because it really describes colliding, and the word coalescence means kind of comes together. So the big ones collide with the little ones, and they make one big happy water droplet, basically. That's collision coalescence. But there's a little bit more to it. I want to kind of describe that. Have you ever, is it coming up here? Have you ever tried to, is there ever been like a feather, like maybe it came from your feather pillow, and you try to get the feather in midair? And that's a tough thing. You're like, because about the time, what's happening with that feather is when you go to grab it, basically just moving your hand like this is basically creating this high pressure, or you want to think of kind of a little wind that actually pushes that feather away. And so with this large droplet getting ready to gobble these little ones, we have the same problem as basically you trying to catch a feather. This big water droplet trying to catch those little water droplets. Basically it creates the high pressure in front of it, a wind, and they all scoot. Okay, so there is a degree of efficiency that can be calculated. Let's see how that goes. So here's what this looks like. So there's your large collector drop going faster than the little baby droplets. And it wants to collide and coalesce. Well, it might collide, may or may not collide, because of kind of we'll talk more about the high pressure that it creates this high pressure in front of it, which is basically then a wind that kind of scoots the little guys. Okay, so that's just kind of the battle that the collector droplet fights in order to successfully collide so it can coalesce. Very similar to trying to catch a feather in midair. So these are 4 frames here to kind of show you the collision and coalescence, getting larger process. So you see the little ones, the big ones falling faster than the little ones. Okay, so you see obviously the collector droplet is getting larger. Okay, I've seen a video of this, and actually this thing can kind of start to oscillate if it gets too large. Rain droplets are not as much a tear shape. They're not tear shaped at all. They're basically, they kind of look like a throat lozenge with kind of, they're dipped in the center and kind of thicker, and they're like a donut. It's not, doesn't have the holes complete. And they get kind of flimsy, and then you see the thing kind of oscillate and break apart, and voila, instead of 1 large collector droplet, we have 5 moderately large collector droplets. That class is not new tonight. Okay. Is there anything posted on the door?
I didn't look, but I would assume that they all have it.
No way.
Bro.
What the?
Not gonna have it. So, we talked about cold clouds, right? Bergeron process. We talked about warm clouds, totally collision coalescence. And now we get to talk about something kind of in between. Okay, cool clouds. Okay, where basically you can have the Bergeron in the upper part of the cloud, Bergeron process, and the collision coalescence happening below. Quite proper, right? Yeah. All right. So some different phenomenon related with precipitation. Cloudburst is basically when the cloud all of a sudden kind of dumps its precipitation all at once. With this dumping, we're going to actually talk, when we talk about severe weather, with precipitation happening all at once, basically that can create a dangerous downdraft known as downbursts. Okay. Another thing associated with, and this actually is a term that made it to your review sheet for your exam, is this one called Virga. And I don't know if you've ever kind of seen in the distance, or this wouldn't have to necessarily be in the distance, but normally clouds have nice flat bottoms. That's the lift and condensation level. Basically, these clouds are dripping. They're actually precipitating, but notice no one at the ground is getting wet. That's because basically the air is pretty dry around it, and it goes ahead and evaporates before it gets to the ground. That's called Virga. So in general, from the collision coalescence process, of course, we get liquid water that hits the ground. You've heard these terms. We have rain. Something smaller than rain is drizzle. Something smaller than drizzle is mist. Okay. Then these are all forms of solid precipitation. Not necessarily precipitation, because rime is not a precipitation, but okay. So we talked last week the different temperature profiles that if, for instance, if something starts out as snow, but it gets warmer as it gets to the ground, it melts and forms rain, right? Okay, but if it's cold enough all the way from the base of the cloud to the atmosphere, you're going to go ahead and get your snow. It's kind of an assortment of things, information about snow. I meant to look it up, but I just think it's really interesting that there's different types of snow. Some are denser, some have more higher water content, some have less water content. A lot of times actually it has to do with the temperature under which the snow is forming. So I snagged this off of the internet, this figure. So kind of the different types of snow crystals that you get at the different temperatures. Dry, powdery snow that's not good to make snowmen from. Right over there. So, just some pretty pictures. So when we talked about different forms of precipitation, we talked about snow, and it's cold all the way from the cloud down to the ground. We talked about rain, which basically it can start as snow and then melts, so we get it as rain. Then we talked about two things, freezing rain and glaze, okay? And sleet, I guess I should say. Freezing rain and glaze are the same thing. Sleet is something a little bit different. But what they both have in common is that they will form if you have a temperature inversion in place. And a temperature inversion is basically, and this did make it to your test, temperature inversion is that if you go up in elevation, it gets warmer. I think on my review sheet I said, or on the, you can think of it as kind of a warm pocket of air above cold. Okay, and so what that obviously allows the precipitation to do is basically fall as snow, melt into liquid, and then refreeze at the Earth's surface. And we talked that depending upon the depth of the temperature inversion, if it's real deep, you'll get sleet. If it's like this, if it's not very deep, you're going to get freezing rain or glaze. All right. So one of the things purposefully we did not include in precipitation last week was hail. So hail, actually, we're going to talk a lot about them just briefly here. Well, not a lot, but hail actually falls from storm clouds. And as some of you guys know, of course, that's cumulonimbus clouds. And there's no straight track for hail. I'm going to show you a picture of the formation of hail within a cumulonimbus cloud. But basically, like I said, it doesn't fall like we saw ice crystals form, the Bergeron process, collision coalescence process. So this is what's happening in a cumulonimbus cloud to give us hail. So you kind of see this blue trip right there. That actually is kind of the up and down is something that ultimately can become large enough so it can actually overcome the updraft that's underneath that cumulonimbus cloud and fall from the cumulonimbus cloud in a piece of hail. So some hail pieces, actually you can see the number of trips it's been around. You know how like you look at tree rings, you can see how many years it's lived. You can see the number of rings around this in there to see how many trips it's been up and down.
Really?
Yep. So we talked about terminal velocity, and this actually is showing you kind of some typical terminal velocities of an assortment of sizes of hailstones. The largest one up here is 3 centimeters, and it falls when it hits the ground at 77 miles per hour. You know, thus the sad car salesman people. So rime, I kind of called this in our review session fancy frost. This is your fancy frost. And they had a good question the review session. So if it has to do with supercooled water, then are these surfaces then just kind of allowing these surfaces providing a surface for that supercooled water to go ahead and crystallize? So I've only seen rime a few times, and it's just beautiful. You see things coated with these. All right, so let's talk measuring precipitation. These are all to measure liquid precipitation. The simple rain gauge versus the rain gauge with a funnel on it. These two actually would be great for some sort of the ASOSs we talked about, kind of automatically getting a gauge on the amount of rainfall. So from left to right, you see the simple rain gauge, you see the rain gauge with the funnel, and then that one over there is basically it collects a certain amount of water, and then it tips all the way over, dumps the water, and then it will go back and forth, and it will count the number of toggles kind of going back and forth. Kind of clever. Okay. This one down here is a rain gauge that has some wind blocks around it to try to kind of prevent the liquid from splashing out. In order to try to get how much rain has fallen, as you might imagine, it's kind of a tough thing. And here's some of the things that you're up against. In terms of being wrong, rain gauges are usually biased low. The amount of rain that really fell. So, measuring snow. That's a tough thing to do too, especially if it blows a little bit. You're like, how much snow did you get last night? I don't know. It kind of blew. But there's the old adage of if you have 1 inch of rain, and if that rain fell as snow, how many inches of snow would that be? And it goes anywhere from like 30 inches of snow for every 1 inch of rain to only 4 inches of snow for 1 inch of rain. So in general, you can think that you lucked out if you get 2 inches of rain. I guess that would have been about 20 inches of snow. So that's kind of how that goes. So this is kind of an introduction to radar a little bit. Of course, if you're kind of used to looking to see what the weather's doing or going to do, you're used to looking at these radar maps. Actually, this is a composite of lots of different little radar stations working together, because radar doesn't carry that far. So basically what these stations do is send out a signal and look for the echo back. And if no echo comes back, there's no precipitation. If an echo comes back, and depending upon the strength of the echo, they can say, oh, it's precipitating out there, and this is how heavy it's precipitating. So it's kind of a joint effort. So there actually is on Netflix, or I don't know if it's still on there, you know how they kind of cycle things on and off of Netflix, but there was a documentary on weather modification I watched. It was very interesting. Okay, so we're just going to briefly talk about ways that folks could try to modify the weather, what's happening around them. Good luck with that, right? Well, one is they can actually use energy. An example of that would be to power a helicopter to try to get air cycling. Okay, warm air down, cool air up maybe. Another one is a little more subtle. We talked about the localized convective heating or localized convective motion, uplift, okay? Basically, that just makes use of the fact that there's a chunk of ground that's a little bit warmer than its surroundings. It's going to get, and you can kind of have some convective motion there. So that's a possibility. Another one is to maybe try to trigger events like precipitation. And actually, I have a slide coming up about cloud seeding. The jury's a little bit out with regard to cloud seeding, whether it's successful and whether it's ethically correct. Okay, so here's my couple of slides about cloud seeding. Looks like a crop duster, but instead of chemicals for field, actually these are chemicals with little cloud condensation nuclei, kind of hoping to try to get the party started where there is not a party. That's to get condensation occurring where there's no condensation. Hygroscopic cloud condensation nuclei. So like I said, cloud seeding, does it work? Not quite sure. And is it correct? No. You know, if we grab the water from moisture from the air here, is that correct for people downstream? So again, cloud seeding. This kind of takes these clouds almost look, I read, like they're temporary. They don't stay very well. So another weather modification would be to, and actually this is on your test, to control those hailstorms, you know, the hailstones that fall. And thoughts there would be disrupting the formation of hail with loud noises or seeding the cumulonimbus clouds. Notice on this slide I kind of said there's no really scientific evidence that either of these have worked to avert the formation of hail. But when we start to talk about severe weather and you know the severe weather warnings that come out, those actually can be issued because of the size of hail. Those severe weather warnings can be issued because of strong winds or the site of a tornado. So, this is an old-timey thing, a noisemaker that was supposed to hopefully kind of stop it from hailing. Not maybe so much, snake oil sounds good. And this is why you want to stop it, the hail from coming down, because of the damage it can do to crops. So the last slide, talking about how can you save those precious crops, okay? Assuming you want to save them from cold temperatures. There's an assortment of ideas here. One is that you can cover them, and hopefully when you cover them, then that outgoing terrestrial radiation will be blocked, so you kind of keep them nice and warm. Another one would be to add heat, okay? Another one, this one I think is interesting, you can try to add a little bit of water on them and hope that that water freezes. And in that liquid water freezing, actually there's a certain amount of energy that's released, like 80 calories, right, of energy is released when liquid water freezes. Another one is just to try to, if we're losing, or try to mix the air and get the warm air circulating to where it's, to the crop that you want to protect. All right, so I know we just got here, but let's take a short break because, as I said, it's going to be kind of a short evening. Hopefully your food will come.
Well, I hope so, I'm hungry.
Same.
Okay, so about 15 minutes or so.
This